Our video tutorial is about principle of mathematical induction. According to the principle, for each n element of natural counting numbers, suppose P of n is some statement involving n if 1, P of 1 is true, and for any key element of n, if P of k is true, then P of k plus 1 is also true. Then P of n is true for all n element of natural numbers. For example, prove that for any positive integer n, 1 plus 3 plus 5 plus up to 2n minus 1 is equal to n squared. Okay. First step, let P of n be the statement 1 plus 3 plus 5 up to 2n minus 1 equals n squared. Then let n equal to 1. So replace n with 1. Since n is only 1, we take 1, bring down, bring n squared, bring down, substitute 1 with n, simplify, so 1 equal to 1 is true. Next, we assume that P of n is true when n is equal to k. So replace n with k. Then we assume that, or we must show that P of n is true when n is equal to k plus 1. Replace n with k plus 1. Okay. We add one more term here because k this time is k plus 1, and replace k with k plus 1. Take note that this series is equal to k squared. So replace it with k squared, bring this down. Okay, distribute 2 times k plus 2 times 1, and 2 minus 1 is 1. Then this is a perfect square trinomial. So they are true. So we have proven that P of n is true when n equals k plus 1. Therefore, by principle of mathematical induction, P of n is true. Next, prove using mathematical induction this statement 1 square plus 2 square plus 3 square up to n square is equal to this fraction for any n element of natural numbers. First step, let P of n be the statement. Then let n equal to 1. So take one element, 1 square, then bring this down. Substitute n equal to 1. So 1 plus 1, 2, 2 times 1 plus 1 is 3. 2 times 3 times 1 is 6. 6 over 6 is 1, which is true. Next step, we assume that P of n is true when n equal to k. So we replace n with k. So this n replace with k. Next, we must show that P of n is true when n is equal to k plus 1. So n here is replaced with k plus 1. So we have to add one term because k this time is k plus 1 and n is k plus 1. So n is k plus 1 is k plus 2. This is replaced with k plus 1. Then we simplify the left side of the statement. Take note that this series up to k square is equal to this fraction k times quantity k plus 1 times 2k plus 1. Bring this down. Then simplify this right side. And we have to verify if the left and right side of the statement are equal. Okay, so this is 2 plus 1 is 3. Then, okay, what we did here is we combine these two terms into a single fraction. So we have here a factor of 6. Then we have to manipulate by factoring to find out if this left is equal to the right in our statement. Take note that k plus 1 is common in both terms. So factor out k plus 1 outside. What is left is k times 2k plus 1. Here is 6 times quantity k plus 1. 1 minus 1 is 1. Then distribute k. K times 2k plus k times 1. This one distribute 6. So we have here 2k square plus k plus 6k plus 6. Then we have to combine these similar terms. K and 6k is 7k. Then factor out this quantity. The factor of 2k square is k times 2k. The factor of 6 is 2 times 3. We verify that the middle term 7k is obtained by multiplying these two quantities. Okay, so we have verified that the left and right side of the statement are equal. So thus Pn is true when k is equal to k plus when n is equal to k plus 1. Therefore by PMI, P of n is true. Next sample. Prove using mathematical induction. 1 cube plus 2 cube plus 3 cube plus n cube is equal to this fraction for any n element of natural counting numbers. First step, let Pn be the statement. Then let n equal to 1. So we bring this down 1 cube. And this right side with n replace with 1. Simplify. 1 plus 1 is 2 square. 1 square is 1. Then 2 square is 4 over 4. Then 1 equals 1, which is true. Then we assume that P of n is true when n equals k. So we replace n with k. Here n is replaced with k. Then we must show that P of n is true when n is replaced further with k plus 1. So we have to add one more term because k this time is k plus 1. And n is k plus 1. Here n is k plus 1. And so with the right side of the statement, so n is k plus 1 is k plus 2. Then we work out on the left side of the statement. We know that this series is equal to k square times quantity k plus 1 square over 4. So replace this with this fraction and bring this down. Then simplify. Combine this into a single fraction by multiplying this quantity with 4. Then take note that k plus 1 square is common to both terms, so we factor it out. So what is left is k square plus 4 times k plus 1. 3 minus 2 is 1. Then distribute 4. 4k plus 4. And this trinomial is a perfect square. So we notice that the left and the right side of the statement are equal. So thus P of n is true when n is equal to k plus 1. Therefore by principle of mathematical induction, P of n is true. Next, prove that n squared plus n is divisible by 2 for any positive integer n. Okay, basis step. Let n equal to 1 and replace n with 1 in this statement. So 1 square is 1 plus 1 is 2. So 2 is divisible, of course, by 2. Next, inductive step. Let key element of natural numbers. Assume the inductive hypothesis that is key square plus key is divisible by 2. Now we show that key plus 1 square plus key plus 1 is divisible by 2 as well. Meaning we replace n with key plus 1. Now we can write key square plus key, which is divisible by 2, with 2m. So in other words, key square plus key is equal to 2m for some positive integer m. Because in our previous statement, key square plus key is divisible by 2. So we have here a factor of 2. Now, this key plus 1 square plus key plus 1, expand this. This is key square plus 2 key plus 1 plus key plus 1, removing the parenthesis. We can combine key square and key here. And positive 1 and positive 1 is 2. So we have 2 key plus 2. Take note that key square plus key is equal to 2m. So replace it with 2m. Bring this down. 2 is common in each term. So factor out 2. So where m and k are positive integer. So this quantity or this expression is divisible by 2. This proves that key plus 1 square plus key plus 1 is divisible by 2. Okay, next example. Prove using mathematical induction. 2 plus 2 square plus 2 cube plus 2 to the n equals 2 to the n plus 1 minus 2 for all n element of natural counting numbers. First step, let P of n be the statement. This statement becomes P of n. Then, our usual step, n equal to 1. So take 2 down and n replace with 1. So 2 to the power of 1 plus 1 minus 2. Simplify this one. 2 square is 4. 4 minus 2 is 2. So that is true. The left is equal to the right. Next, we assume that P of n is true when n is equal to key. So replace n with key. This is replaced with key. Okay. Then we have to show that P of n is true when n is replaced with key plus 1. So we have to add one more term because we add plus 1 to key. So key is, this n is replaced with key plus 1. So key plus 1 is key plus 2. Next, we observe that this series up to 2 to the power of key is equal to 2 to the key is 1. We replace this portion of the series with 2 to the key plus 1 minus 2. Then bring this down. Okay. Then observe that these two terms are equal. So we can combine them. There are 2 of them. Or 2 to the first power times 2 to the key plus 1. We have to add, multiplying the same base, add the exponent. So key plus 1 is 2 to the key plus 2, which is equal to the right side of the statement. So thus P of n is true when n is equal to key plus 1. Therefore, by principle of mathematical induction, P of n is true. Next, prove using mathematical induction. 4 to the n minus 1 is divisible by 3. for any n element of natural counting numbers. Step 1. Let P of n be the statement 4 to the n minus 1 is divisible by 3. Then, let n equal to 1. So, substitute n with 1. 4. The rest of the first power is 4 minus 1 is 3, which is divisible by 3. Next, we assume that P of n is true when n is replaced with key. N is replaced with key. So 4 to the key minus 1 is divisible by 3. Then we must show also that P of n is true when n is replaced with key plus 1. So 4 to the key plus 1 minus 1 is divisible by 3. Okay, this is an exponential form. We can separate this by 4 to the key times 4 to the first power. Next, from our statement, 4 to the key minus 1 is divisible by 3. Let it be equal to 3m for some positive integer m, because this is divisible by 3, so one of its factor is 3. Then solve for 4 to the key. Transfer negative 1 to the right becomes positive. After that, this 4 to the power of key is replaced by 3m plus 1. 3m plus 1 times 4 minus 1. Distribute 4. 12m plus 4 times 1 minus 1. 4 minus 1 is 3. Take note that 3 is common in these terms, so factor out 3. So 3 times quantity 4m plus 1, which is divisible by 3. Therefore, P of n is divisible by 3.